Right now, 15 billion miles from where you're sitting, a machine the size of a small car is flying through the dark at 38,000 miles per hour. It's been doing that for 46 years. And in November of 2023, it stopped making sense, not stopped transmitting. That's the thing people keep getting wrong. The signal was still there, strong and clear, arriving on schedule the way it had for nearly 5 decades. But the information riding on that signal had turned into pure noise. Ones and zeros arranged in a repeating pattern that meant absolutely nothing. Engineers at NASA's Jet Propulsion Laboratory were receiving a perfect carrier signal from the most distant object humanity has ever launched, and they couldn't read a single word of it. 5 months passed like that. Here's the part the headlines weren't telling you. Voyager 1 isn't just a spacecraft doing science for the sake of curiosity. It's the only working instrument in existence that is physically located in interstellar space, the actual space between star systems, taking real measurements from a region no other machine has ever reached. What it's been finding out there doesn't just affect scientists at JPL. It directly affects how well our solar system protects you from radiation pouring in from the rest of the galaxy. When Voyager went silent, humanity lost its only set of ears at the edge of everything. And honestly, the fact that it went silent the way it did, quietly, still transmitting, still apparently functioning, made it worse. Nobody knew how bad the situation really was until they sat down and looked properly. If this is the kind of story you want to keep getting, hit subscribe and turn on notifications. We cover the space discoveries that actually matter every week. Voyager 1 launched September 5, 1977. The mission plan called for 5 years. Engineers would fly it past Jupiter and Saturn, gather data on the gas giants and their moons, and that would be that. The computers on board were custom-built by General Electric, 68 kilobytes of total memory spread across 3 separate machines. A modern smartphone carries roughly 100 billion times more processing power than those computers combined. Nobody building those chips in 1977 expected them to still need to function in 2023. Nobody was thinking that far ahead, because nobody imagined the mission would still be running. Jupiter came first, in March of 1979. Voyager found active volcanoes on Io, one of Jupiter's moons, which genuinely shocked the scientific community, because before that moment, Earth was the only place in the solar system known to have active volcanoes. That single discovery alone changed how scientists thought about geological activity across the solar system. Then Saturn in November of 1980, close enough to study the ring structure in detail that had never been possible from Earth. After Saturn, mission controllers used the planet's gravity as a slingshot and deliberately threw Voyager onto a trajectory that would carry it permanently out of the flat plane of the solar system. There was no coming back from that. It wasn't an accident or a miscalculation. It was the plan. Voyager 1 was going to keep flying until there was nothing left to fly through, and then it was going to keep flying anyway. August 25, 2012. After 35 years of travel, Voyager crossed the heliopause. That's the boundary where the sun's solar wind, the constant stream of charged particles flowing outward from the sun, finally loses the battle against interstellar pressure and stops pushing back. Crossing it meant Voyager had entered interstellar space, the actual space between the stars. No human-made object had ever been there before. The confirmation came from Voyager's plasma wave subsystem, detecting a sharp jump in plasma density exactly where theoretical models predicted the boundary should sit. The models held. The boundary was real, and now Voyager was on the other side of it. And then, in May of 2021, something turned up in the data that changed what scientists thought they were actually listening to. Stella Koch-Acker was a doctoral researcher at Cornell University, working through years of Voyager's plasma wave recordings when she found it. Not a burst, not a glitch triggered by some solar event. A continuous, faint, steady tone, narrowband, monotone, persistent across years of data, sitting underneath all the louder solar-driven signals like background rain that never stops. She called it a plasma hum. What Voyager's instrument was picking up was the sound of interstellar gas, ionized particles left over from stars that died millions of years before our sun was born, oscillating at their natural frequency as the spacecraft drifted through them. Her paper published in Nature Astronomy on May 10, 2021. Senior co-author James Cordes, the George Feldstein Professor of Astronomy at Cornell, described what they were hearing like this. The interstellar medium is like a quiet or gentle rain, and solar events are the thunder. But between the thunder, the rain never stops. Ocker put it simply in the paper itself. We're detecting the faint, persistent hum of interstellar gas. That hum was the first continuous direct measurement of interstellar plasma density ever recorded by any instrument anywhere. Before Voyager, everything scientists knew about the space between the stars was theoretical. Models, calculations, educated guesses about what the gas density was, how the magnetic field behaved out there, how the boundary between our solar system and the rest of the galaxy was actually shaped. Voyager turned those guesses into measured numbers. Real, specific, verifiable data points from a machine that was physically sitting in the middle of that space, drifting through it, listening to it. But what those numbers implied, that's where it got uncomfortable. And that part barely made the news at all. The plasma hum wasn't just interesting physics. It was telling scientists something specific and troubling about the heliosphere's shape. The heliosphere is the protective bubble the sun's magnetic field and solar wind create around our entire solar system, the thing that shields Earth from the harshest cosmic radiation flooding in from the rest of the galaxy. The density of interstellar plasma pressing against the outside of that bubble directly affects how the shield is shaped and how thick it is at any given point. And what Voyager was measuring didn't match the existing models cleanly. Voyager 1 and Voyager 2, which crossed the heliopause in November of 2018 on a completely different path through the southern part of the solar system's outer boundary, were finding different conditions at the boundary on their respective trajectories. Different plasma densities, different magnetic field orientations. The heliosphere wasn't the neat, symmetric bubble that the models had assumed for decades. It was asymmetric, uneven. Scientists had to go back and fundamentally rethink what they understood about the shape of the thing that protects every living creature on this planet from galactic radiation. Nobody broke that story the way it deserved. Genuinely, 5 research papers came out in that period, and the coverage outside specialist journals was almost nothing. What Ocker's plasma wave data was telling scientists in practical terms is this. The plasma density Voyager measures continuously in interstellar space is the single most important input into models of the heliosphere's shape and strength. Higher plasma density outside means more pressure on the protective bubble from the galaxy's side. Uneven pressure from different directions means an uneven shape, and an uneven shape means some directions offer less protection from incoming cosmic radiation than others. Voyager 1 and Voyager 2 between them had now confirmed that the heliosphere is shaped differently on one side than the other. The implications for how much galactic radiation reaches the inner solar system are still being worked out. The models are being rewritten right now, using Voyager's measurements as the primary inputs, and those measurements can't come from anywhere else. There is no other instrument in interstellar space. There never has been. The hum that Ocker found wasn't just an interesting discovery about gas between the stars. It was the only continuous readout humanity has ever had of how hard the galaxy is pushing on the thing keeping Earth habitable. So when Voyager went silent in November of 2023, that's what went dark. November 14, 2023. The signal changes. The carrier wave stays strong and the probe is clearly still receiving commands. Mission controllers test that immediately. But the data stream, the actual content being transmitted, becomes a repeating pattern of ones and zeros that don't correspond to any recognizable telemetry format. The flight data subsystem, one of 3 onboard computers, and the one responsible for collecting readings from all the science instruments, packaging them, and handing the bundle to the radio transmitter for transmission to Earth, has stopped producing readable output. Engineers at JPL start running diagnostics. They try restarting the computer remotely. The problem doesn't clear. They start working through old engineering memos, documents written in the 1970s, looking for clues about how a computer architecture that no longer exists in any modern documentation actually behaved under fault conditions. Linda Spilker, Voyager's project scientist, described the process later. We had some people left that we could rely on who could remember working on bits of the hardware, but a lot of it was going back through old memos, like an archaeological dig to try and find information on the best way to proceed. Every single diagnostic command took 45 hours round trip. Voyager is so far from Earth that radio signals, traveling at the speed of light, take 22.5 hours just to reach the spacecraft. Then another 22.5 hours for the response to travel back. Engineers would send a command on a Thursday and wouldn't know if it had done anything useful until Saturday. That's the reality of operating the most distant spacecraft in human history. March 3, 2024. The team sends what they internally called a poke, essentially an instruction telling the flight data subsystem to dump its own memory contents back to Earth. What came back wasn't properly formatted telemetry. It was, well, not usable science data exactly, but not random noise either, and that difference mattered enormously. A Deep Space Network engineer, working carefully through the partial readout, decoded it. And what it showed was that approximately 3% of the flight data subsystem's memory had been corrupted. One chip, a single RCA CD4061A CMOS static RAM chip holding 256 words of memory, had failed, possibly struck by a cosmic ray during its 46 years in deep space, possibly just worn out from age. That chip contained a section of the computer's own operating code. Without that code intact, the computer couldn't package data correctly, couldn't format it, couldn't make it readable. So it kept sending, kept working as hard as it ever had, but everything coming out was nonsense, still transmitting. Still, after 46 years, the chip couldn't be replaced. Nobody can send a repair crew to 15 billion miles of distance. So the JPL team, with project manager Suzanne Dodd running the mission as she has since 2010, devised something else entirely. They would relocate the damaged code, break the affected section of software into smaller pieces, rewrite each piece so it could live in a different spare corner of the flight computer's 68 kilobytes of total memory, and then add new cross-references between the pieces so the fragments would still communicate with each other and function as one program. It took, well, not a simple patch exactly, more like digital surgery on a patient you can only observe through a photograph that arrives 2 days after the picture was taken. The fix was transmitted April 18, 2024. 22.5 hours later, it arrived at Voyager. Engineers waited through the following day. April 20th, the response came back. The data was readable. All of it. The JPL team gathered in a conference room in Pasadena and confirmed it, quietly, the way engineers celebrate when something worked that had no business working. By June 13, 2024, all 4 of Voyager's remaining science instruments were sending usable data for the first time in 7 months. Now, stop. You're breathing air right now. The specific radiation environment you're sitting in, the level of galactic cosmic rays reaching Earth's surface at this moment, is the direct result of the heliosphere working correctly, deflecting a significant portion of incoming radiation before it ever reaches the inner solar system. Galactic cosmic rays are high-energy particles accelerated by supernova explosions and other violent events happening all across the galaxy, constantly. Without the heliosphere blocking most of them, they'd hit Earth's atmosphere in far greater doses. They penetrate aircraft at cruising altitude already. They damage satellite electronics. At high enough exposure levels, they increase cancer risk in anyone exposed over time. Astronauts on long missions outside Earth's magnetic field worry about galactic cosmic rays constantly because the radiation environment in deep space is one of the hardest unsolved problems in human spaceflight. The heliosphere deflects somewhere between 70 and 90% of incoming galactic cosmic rays before they get anywhere near the inner solar system. How effective it is depends on its shape, its thickness, its magnetic field structure, and those things depend on the interstellar environment pressing against it from outside, which is exactly what Voyager's plasma wave subsystem was measuring. The Stella-Ocker found was a continuous readout of how hard the galaxy is pushing on the only shield standing between Earth and full exposure to the radiation environment of the Milky Way. If the heliosphere is thinner or more asymmetric than current models account for, cosmic ray exposure on Earth is higher than those models predict. Nobody at NASA is saying the situation is currently dangerous, but nobody can say it isn't going to matter on longer timescales without Voyager's data. And Voyager is the only instrument that exists in the location where that data can be collected. So when it went silent for 7 months in 2023 and 2024, that wasn't a technical inconvenience. That was 7 months of irreplaceable measurements that are now gone permanently. Here's where things stand as of August 2026. Voyager launched with 10 science instruments in 1977. As of April 17, 2026, only 2 remain powered on. The mission team at JPL shut down the low-energy charged particles experiment on that date, a deliberate decision made to conserve power, not a hardware failure. Mission manager Kareem Badaruddin explained it directly. While shutting down a science instrument is not anybody's preference, it is the best option available. Before that, the cosmic ray subsystem went dark on February 25, 2025. The power budget is that tight and getting tighter every single year. And here's something worth sitting with for a moment. Voyager 1 carries a golden record, a 12-inch gold-plated copper disc containing sounds and images selected to represent life on Earth, put together by a committee that included Carl Sagan. Music from different cultures, greetings spoken in 55 languages. The sound of rain, the sound of surf, a mother's first words to a newborn child. It's been flying through the dark for 46 years, now in interstellar space, and it will keep flying long after the last instrument goes dark and long after the last engineer who worked on the mission is gone. It will drift through the galaxy for billions of years carrying that record, and there's almost certainly nobody out there to find it. But scientists put it on there anyway. That detail matters because it tells you what kind of mission Voyager actually was. It was never just about data. It was about the fact that humanity was willing to send something into the permanent unknown and put everything that mattered about us on it, just in case. What's keeping Voyager 1 alive right now is heat from decaying plutonium-238 converted into electricity by 3 radioisotope thermoelectric generators. Those generators have been losing roughly 4 watts of output every year since launch. As of 2026, they're producing less than half their original power output. Engineers have been switching off heaters and instruments in a carefully calculated sequence because in the negative 270 degrees Celsius environment of interstellar space, letting the wrong component get too cold means it freezes, cracks, and fails permanently. There's no margin for error at this point. Every decision about what to turn off next is a calculation about what Voyager is still allowed to sense as it flies. What remains running right now, the magnetometer, measuring the magnetic field in interstellar space. And the plasma wave subsystem, the same instrument that found the hum, the one still listening to the sound of the gas between the stars. On November 18, 2026, Voyager will reach exactly 1 light day from Earth. A signal sent from Earth that day will take a full 24 hours to arrive at the spacecraft. No object humanity has ever launched has been that far from home. The engineering team at JPL is currently working on something they're calling the Big Bang, a final software upgrade designed to squeeze additional operating life from the probe, potentially keeping the plasma wave instrument and the magnetometer running deep into the 2030s. It hasn't been confirmed as implemented yet. The team is still working on it, and the window to execute it is narrow. Sometime in the 2030s, if the Big Bang upgrade succeeds in buying the maximum possible time, the power will fall below minimum operating threshold. NASA will switch off the last instrument. The radio transmitter may keep sending engineering heartbeat data for some additional time after that. But the science mission will have ended. No more magnetic field measurements. No more plasma wave detections. No more hum from outside the boundary of the solar system. And there is no funded replacement mission. The interstellar probe concept, a dedicated spacecraft designed from launch to follow Voyager's path and continue its measurements, has been studied in detail by NASA and evaluated by the scientific community. It remains unfunded and unscheduled as of 2026. A spacecraft launched today would need decades to reach where Voyager currently operates. When Voyager goes quiet, the only direct in-situ measurement window humanity has ever had on interstellar space will close, possibly for the rest of your lifetime. Possibly longer. A machine built to operate for 5 years, now in its 47th year of flight, is the only instrument standing between humanity and complete ignorance about what the space between the stars actually does to the boundary protecting this planet. It broke in November of 2023 in a way nobody had encountered at that distance before. Engineers fixed it by rewriting its software from 15 billion miles away using 46-year-old internal memos as their only reference material. And when it came back online, the plasma wave instrument was still detecting the hum that barely anyone reported properly when Stella Ocker first published it in 2021. The comparison that comes up in the scientific literature is the Hubble Space Telescope repair in 1993, when NASA sent astronauts up to fix a flawed primary mirror that had been producing blurry images since launch. That repair required a physical crew, spacewalks, new corrective optics installed by human hands during a mission that took 11 days. Hubble was 340 miles above Earth. The Voyager repair in 2024 required none of that. No crew, no hardware. Just engineers in Pasadena reading through 40-year-old internal memos, trying to understand how to talk to a computer architecture that exists nowhere else in the world anymore, and then waiting 45 hours to find out if anything they sent actually worked. The Hubble repair was covered by every major broadcaster on the planet. The Voyager repair was, by comparison, almost invisible in mainstream coverage, which tells you something honest about what gets treated as a story and what gets buried under the next news cycle. Because what Voyager is doing right now, in August of 2026, is not finished. It's still out there, still flying at 38,000 miles per hour, still listening. The plasma wave subsystem is still sending back density measurements from a region of space that no other instrument has ever sampled from the inside. Every data point it transmits is the only data point of its kind in existence. Every day it keeps working is another day scientists have something they genuinely cannot get from anywhere else. The hum is still there, steady, narrowband, persistent. Voyager is still listening, for now. If this story landed differently than you expected, subscribe and turn on the bell. We don't flatten these discoveries into headlines. Drop your thoughts in the comments below. When Voyager's final instrument goes dark, what do you think we'll have missed the most? Because that's the question nobody on the Voyager team has a clean answer to right now.